Welcome back, everybody. We're going to talk in this video about a certain type of calculation that I think will eventually help us to really understand what equilibrium is. We're going to start off simple and get a little bit more complicated. In this first calculation, we're going to look at just a forward reaction or a forward change if I was looking at the reaction between A and B in only a left to right or reactant to product direction. I think what's important is looking at your initial conditions for the reaction. So for this reaction, we're going to start with 5 moles of A, but 0 moles of B. The other thing we need to know is how does the reaction actually proceed? What percentage of molecules actually react over a period of time? And so in this particular equation, we're going to suggest, what if 60% of A molecules turned into B molecules on a per minute basis? What would it look like at the end of that particular process? Well, if 60% are going to react, the calculation that I want to do is pretty simple. I'm going to take 5 moles of A and multiply it not by 60%, but by the fraction 0.6. And when I do that, I get 3 moles of A react. Notice I have a negative sign in front of it, though. That's because it's disappearing. It's reacting. It's turning into B. And on the product side, I have that same 3 moles, but they're appearing. And so I have a positive sign in front of it. And so at the end of 1 minute, I am left with 2 moles of A and 3 moles of B. But what if it were more complicated than that? What if I had simultaneous forward and reverse reactions taking place? By the way, before I get to that, I should say the calculation I just did assumes one very important thing, that my coefficients here are in a 1-to-1 ratio. In other words, I lose 3 on this side, I gain 3 on this side. If it were in a 2-to-1 ratio or a 1-to-2 ratio, then the math would look a little bit different and would be a little bit more complicated than this is leading us to believe. All right, second calculation. Let's say that A is going to B, but B is going to A at the exact same time. Again, initial conditions are so important. We're going to say that we're going to start with 5 moles of A, but this time, instead of 0 moles of B, we're going to say we have 2 moles of B. And we're going to calculate forward change and reverse change. This time, again, we're going to say 60% of A molecules turn into B molecules on a per minute basis. But we're going to add an additional percentage here. 20% of B molecules will turn into A molecules on a per minute basis. Now, you could make this math much harder for yourself and probably and definitely incorrect if you overthink it. So what I'm about to say is really, really important. We know that the forward and the reverse reactions are happening simultaneously. And so when we calculate a change forward or a change reverse, we don't need to take into consideration what's going on the other side. I guess what I mean by that is we only need to look at the initial conditions. You'll see what I mean here in a moment. So 5 moles of A are reacting at 60% per minute. That's the same reaction rate that we had before. So we had 3 moles of A disappear on this side and 3 moles actually up here. That should be a positive sign on this side. But now we have moles of B also reacting, 20% of 2. So if I said 2 times 0.2, I get zero point 0.4. I'm going to say, again, I messed up my signs here. I apologize for that. I'm going to say minus 0 0.4 moles of B become plus zero point 0.4 moles of B on this side. Now, if you didn't understand what I was saying before, notice that when I did my change reverse calculation, I did not look at 2 plus 3. In other words, I am assuming that these reverse and forward reactions are happening simultaneously. So at the end of 1 minute, this is what I'm left with. 5 minus 3 plus zero point 0.4. I'm left with 2.40 moles of A. And I'm left with 2 plus 3 minus 0 0.4, 4.6 moles of B. Now, you may have noticed I haven't said that this is actually what equilibrium represents. In fact, it's not. We haven't reached equilibrium yet. So, how do we know when we're there? And what actually is equilibrium? I think we need to kind of bear the brunt of some in depth calculation in order to do that. So, in a moment, you're going to come back to the Google Meet, and in groups, you're going to work your way through a set of initial conditions like we've just done. But instead of doing it for 1 minute, we're going to do it for 2, 3, 4, maybe up to 10 minutes, and then decide what equilibrium actually means. Okay? So I'll see you back at the Google Meet momentarily.